Welcome back to Infinity Physics. In this lecture, we are going to discuss about relation between electric field and potential difference, and also we will derive two equations which relate electric field and potential difference, and also we will discuss about equipotential surface, and then we will solve numericals related to E is equals to minus dV by dr, V is equals to E dot dr, and also related to the equipotential surfaces. So let us start our discussion. Suppose we have a source charge, that is a point charge here, from which electric field lines are coming out, right? So here so many field lines are coming out, but we are considering this line only. So this is the direction of the electric field lines which is coming from it. It is coming in all direction because a point charge has spherical symmetry. So here the electric field is coming in all directions, but we are considering only this direction. So here at some distance, at a distance r, let us say we have a test charge Q naught, right? It's a test charge which we are going to move from one place to another place, or from one point to another point. So here, due to this charge at this particular point, we have some electric potential. Due to this charge at this position, we have some electric potential which is given by V is equals to KQ by R, which is given by V is equals to KQ by R. Similarly, at position B, there is some potential, right? See here, this Q refer to the source charge, right? Again here, so here the potential at point A is VA, and potential at point B is equals to KQ by, this is RA and this is RB, right? Now what we are doing? We are moving this charge from this point to this point. Now let us assume that these 2 points are separated by a very small distance, right? To show you in a good way, I have represented them far apart, right? But actually they are very near to each other, right? So this point of separation is very less, and they are separated by a very small distance dr. So we assume that at both this point the electric field is approximately same, right? So here at these 2 points the electric field is approximately same, not exactly same, right? Now at this point the potential is VA is equals to V. Let us assume that at this point the potential is V, right? So as we are moving towards this side, the potential will increase. Why potential will increase? See here, this charge is exerting some potential here, right? Also here, which charge is near? We know that V is inversely proportional to R. V is inversely proportional to R. So as we come near to the charge, the potential will increase. It's like a spring. अगर आप spring को push करते हो तो क्या होता है? उसका potential बढ़ने लगता है. Similarly here, if you bring this point charge Q naught, that is a test charge, towards this source charge, so if you are bringing towards it, its potential will increase. So the potential will increase by dV. Why dV? Because the distance is very small. So if you are moving a very small distance, the potential will increase by a very small amount. So here potential is V. So here it is V plus dV, because potential is increasing. So plus dV. So by this amount the potential will increase. So we can write, see, when the charge is brought from this position to this position, we are applying the force in this direction. So here the electric field is pushing the charge towards right side, but the displacement, that is the force applied, is in this direction, but the displacement is towards in this direction. We are applying force in this direction, but the force applied by the electric field is towards the right side, right? And the displacement is towards the left side. So the angle is 180. Both are opposite. So here force applied by the electric field is minus Q naught E. We know that, right? E is equals to F by Q. So F is equals to minus Q naught E. Now work done in taking the charge or bringing the charge from A to B, we know that force work is equals to force into displacement. So force is here. Now what is displacement? The displacement is dr. So small work done in bringing the charge from A to B is equals to F dot dr. Now F is minus Q naught E and dr as it is. So this is equation 1, this is equation 2. Also from the formula of the potential difference and potential, we know that V is equals to W by Q naught. We know this relation, where this is the test charge. So here dW, that is work done, is equals to V into Q naught. So work done, small work done, is equals to Q naught delta V. That is potential difference between these 2 points. So work done is equals to charge into potential difference. So dW is equals to Q naught dV. Why Q naught dV? See here. What is VB? VB is V plus, I can write like this here, V plus dV minus VA. What is VA? It is only V. So here this and this will get cancelled. So we are only remain with dV. That is the potential difference between these 2 points. So that is dV. dV is the potential difference. So dW, that is a small work done, is equals to Q naught dV. Now let's compare equation 2 and equation 3. So here dW is equals to minus Q naught E dot dr, and here dW is equals to Q naught dV. So if we compare this, then this and this will get cancelled. So E is equals to, here dV, this minus sign, and dr we can bring here, right? So here dV, here E is equals to dV by dr, this we can bring here. So E is equals to dV by dr, but here minus sign is there, so we can write E is equals to minus dV by dr. Means electric field is equals to the negative of the potential gradient. This term dV by dr is called the potential gradient. Now what is potential gradient? See, gradient indicates 2 things. One, either something is increases with the time or with the distance, or something decreases. If here we have negative sign, see here we have negative sign, so we can call it as a negative of potential gradient or negative potential gradient. That is, with the distance the potential decreases. So here, suppose here the potential is of 20 volt, let us assume that. So at this point the potential will be of 18 volt. So at this point the potential will be of 16 volt. So as you move far away from the charge, that is, as you move far away from the charge, that is in the direction of the electric field. So if you move in the direction of the electric field, the potential decreases with the distance. The potential decreases with the distance. So minus dV by dr is termed as negative of the potential gradient, or it is the negative potential gradient. That is, potential decreases with the direction, with the increase in the distance in the direction of electric field. Minus dV by dr indicates if you move in the direction of the electric field, the potential decreases with the distance. So we have this formula, V is equals to KQ by R. So it is V is inversely proportional to R. So if you move in the direction of the electric field, the potential decreases. That is, change of potential with distance. What potential gradient indicates? Change of potential with distance. Negative sign indicates V decreases with distance. This quantity, see, dV by dr is equals to E. Let us just forget the negative sign, then we know that dV by dr is equals to, it is just for assumption, this for our convenience, right? I am just removing the minus, and if you want to put, you can put also here. See, here E is a vector quantity, so whatever equals to V should be also a vector quantity. So here dV by dr is a vector quantity. dV by dr is a vector quantity, it is not a scalar quantity. But if we talk about only V, only potential, then only potential or potential difference is a scalar quantity, right? So here dV by dr is termed as a potential gradient and it is a vector quantity. And what is the SI unit? See, here we have electric field, so SI unit of this quantity also should be same as the electric field, that is either Newton per coulomb or volt per meter. See here dV by dr, dV by dr means the SI unit of volt is V and SI unit of distance is meter. So the SI unit of dV by dr, that is the potential gradient, is volt per meter or Newton per coulomb, and it is a vector quantity. Keep this in mind. So in the first equation we have obtained that E is equals to minus dV by dr. What does this indicates? The electric field at any point, suppose at this position I am having a positive charge here, so electric field at this particular point is equal to the negative of the potential gradient. See, this whole term is known as potential gradient, right? So negative of the potential gradient at that point. So this distance is r. So electric field at any point is equal to the negative of the potential gradient at that particular point. Now, if I make dV as a subject, then dV is equals to minus E dot dr. Now, if I integrate this equation, so I can integrate dV, that is dV from V1 to V2 or from V1 to V2, right? I can integrate this dV, that is the potential, from this point to this point, that is from V1 to V2. dV is equals to this term E dot dr, I can integrate from R1 to R2. So integrating this term from V1 to V2, this term from R1 to R2, then the integration of dx is x, integration of dy is y. Similarly, integration of dv is v. Upper limit, lower limit is equals to minus r1 to r2 E dot dr. Upper limit minus lower limit, v2 minus v1 is equals to same term, minus integration r1 to r2 E dot dr. Now let us assume that this point r1 is at a very large distance, that is, let us assume that it is infinite. So we are bringing the charge from infinite, that is from distance r1 which is infinite, to here at a point which is at a distance r2, and the potential at that point is v2. So if we take r1 is equals to infinite, then the potential at infinity is 0. We know that the potential at infinity is 0, and r2 is equals to r, and let us assume that the distance r2 is equals to the r, and the potential v2 at this point we assume that it is v. If you want to keep it v2, then you can keep, right? So here we assume that r1 is at infinity, so the potential at infinity is 0, and r2 as a distance r, and potential at that particular point is v. So I can modify this equation. Instead of v2 minus v1, v1 is 0, and instead of v2 I can write v. So v of r, it is not in the multiplication, it is subscript here. So v at a distance r, it is a v of r. So we can say potential at a distance r is equals to minus, see, instead of r1 we have assumed it is infinity, so minus infinity to r is equals v of r is equals to minus integration from infinity to r is equals to E dot dr. So this is our final equation. So either we can use this equation, or if we integrate dr and the integration is r or integration is d, anything, right? Suppose there is a parallel plate capacitor. In this chapter you will learn the capacitors, right? So if there is a two plates, either parallel or cylindrical, so if there is a two plates, so between the two plates, suppose this is two plates, so between the two plates the electric field is uniform, and the distance between the plates is d. So if it is asked to find the potential between the plates, then what you will write? Electric field. The electric field is uniform between the plates. So electric field into distance between the plates. So what is the potential due to these two plates? So it is electric field into distance between the two plates. Or if it is asked what is the electric field, then potential divided by distance, that is E is equals to V by B. This is very important equation. See, you need some practice to know that where to use this equation and where to use this equation. So let us solve some numericals related to this quantity. So it will be easy for you to understand when and where to use these two equations and this also. Question 1. Calculate the voltage needed to balance an oil drop carrying 10 electrons when located between the plates of a capacitor which are 5 mm apart. The mass of oil drop is 3 into 10 to the power minus 16 kg and G is equals to 10 meter per second square. Now according to the given question, we have here a capacitor in which one plate is a positively charged and another plate is a negatively charged. We will discuss more about capacitors after few topics. Okay, so here if you provide a battery here, if you connect a battery here, then this plate will become positively charged and this plate will become negatively charged, and an electric field will establish between these plates of a capacitor. So here we are placing an oil drop. We have kept here an oil drop. Okay, and that oil drop carries 10 electrons. Number of electrons carried by the oil drop is 10 electrons. So Q is equal to, what is the total charge on the oil drop? It is N, that is 10 electrons into charge of each electron. And the distance between this plate is given 5 mm, that is 5 into 10 raised to minus 3 meter. The mass of the oil drop is 3 into 10 raised to minus 16 kg, and as this chalk will fall, then what will happen? Some gravitational force is acting, due to which it gets accelerated. So the value of the gravitational acceleration by which this oil drop will be pulled by the gravitational force is given 10 meter per second square. It is asked that we have to balance this oil drop. So how much voltage we have to provide so that this oil drop will get balanced, right? It's actually sometimes it is asked how much electric field, right? But here it is asked how much voltage. So to balance the oil drop, see, this is our oil drop. Now to balance anything, we need to provide two equal and opposite force. So here what is happening? The gravitational force is pulling this oil drop towards the downside. So if we provide an electric field in this direction, see, then this electric field will push the drop in the upward direction. Why? See here, this electron, it carries 10 electrons. So electrons are negatively charged. So this negative plate will repel this electron and this positive plate will attract the electron. That is, the electric field between the plate will push the negative charge from negative to positive, that is in the upward direction, and the gravitational force will pull this drop in the downward direction. So if these two forces are equal and opposite, then this drop will be in equilibrium. So this is the drop I have represented like this. So in equilibrium, the electric force QE means it is the electric force is equals to the gravitational force, which is mg. So if I make E as a subject, then E is equals to mg by Q. But we know that E is equals to V by D, because it is asked to find voltage, how much voltage needed. That's why we are using this equation. Now put this V by D in place of E. So we can place V by D is equals to M G by Q. What is M? Is given 3 into 10 raised to minus 16. G is given 10 and charge Q is 10 into 1.6 into 10 raised to minus 19. So here we have D, that D if we take this side then it gets multiplied, and the D, that is the distance between the plates. D is the distance between the plates, which is given 5 mm. So here we have placed it. So now this and this will get cancelled, and if you solve this you will get 9.47 volt. That is, to balance this drop we need to provide a 9.47 volt. That is a potential difference between these two plates, so it will get balanced. Now let us solve next question. Question 2. If the potential in the region of space around the point -1, 2, 3 is given by V is equals to 10x square plus 5y square minus 3z square volt, calculate the three components of electric field at the given point in the field. According to the question, we have 3 points which are lying in the space, that is in the three-dimensional coordinates. So here, first point lies at a distance -1 meter from the origin on the x-axis. Another point lies at a +2 meter distance from the origin on the y-axis. And a third point at a distance C. If this is our y-axis, this is our x-axis, then the perpendicular to the board, that is the third axis, that is the z-axis. So this is our z-axis which is actually perpendicular. So this point lies at a distance of 3 meter from the origin on the z-axis. And the potential with the distance, it is given as, on the x-axis it is given 10x square, on the y-axis it is given 5y square, and on the z-axis it is given -3z square. And we need to find the electric field at these all 3 points, that is on the x, y and z axis. At all these 3 points we have to find the electric field. So we know that E is equals to -dV by dr, that we have derived. So I can write d by dr minus d by dr. What is V given? V is given 10x square plus 5y square minus 3z square. Now I want to separate. See here, r is equals to -1, 2 and 3. So this is for x, this is for y and this is for z. So now I am separating all these terms. So for Ex, I want to calculate the electric field on the point on the x-axis at a distance of -1. So if I want to calculate at the x-axis, I need to differentiate this equation. I need to perform differentiation with the x coordinate. So d by dx of this equation. See, sometimes may here lie y square into x, 3z square into x or anything, right? So we need to differentiate all equation with respect to x. So Ex is equals to -d by dx. For Er, we write -dV by dr. So for Ex, we can write -d by dx. Now on differentiating this term with respect to x, we get, see here, it is 10x square. So on differentiation, we will get 2 into 10, right? 2 into 10 into x. So 20x, but here we have negative sign here. See here we have negative sign. So it is -20x plus, here we don't have any x, and here. So here differentiation of this y and z with respect to x is 0. So here we get Ex is equals to -20x. Now what is x given? X is given -1. So here if we put in for x is equals to -1, we get -20 into -1 is equals to 20 volt per meter or 20 Newton per coulomb. That is, at this point the electric field is 20 Newton per coulomb. Similarly for y, right? So Ey is equals to, again we can write Ey is equals to 10 d minus d by dy. See here, instead of r, now we are substituting y. So E of y is equals to -d by dy of 10x square plus 5y square minus 3z square. Again here we have y. So differentiation of x and z will be 0. So we are remain with -d by dy of 5y square. So now again differentiation of y square with respect to dy, we get 2 into 5, that is 10y, and minus sign is there. So Ey is equals to -10y. But y is equals to 2 is given here. So -10 into 2 is minus 20 volt per meter or minus 20 Newton per coulomb. That is, electric field at this point from origin is minus 20 volt per meter. Similarly, for Ez, we need to differentiate this equation with respect to z. That on differentiation of minus 3z square with respect to z. So again this 2 will come here. So 2 into 3. But here it is minus 3. So minus 6z and minus sign here. So it is minus 6z. Minus plus. So Ez is equals to 6z. Now what is z given here? 3. So 6 into 3 it is 18. So the electric field at this point, that is from the origin at a distance of 3 meter, the electric field is given 18 Newton per coulomb or 18 volt per meter. Now let us try next one. Question 3. Electric field E is equals to 20 I cap plus 30 J cap Newton per coulomb exist in free space. If the potential at origin is taken 0, determine the potential at point A 2, 2 meter. According to the given question, the electric field is given as 20 I cap plus 30 J cap in the region of free space. So, its magnitude is larger in the direction of Y and smaller in the direction of X. So, I have represented it like this. And we have to find the electric field at point A, which is given 2, 2. That is 2 here. 2 meter in the X direction and 2 meter in the Y direction. So this point will lie here. If you join this, then this point is lying here, which is given as 2, 2. And the electric, the potential at origin is 0. So we need to find the potential at point A. So here we have to find the net potential. So how we can find? We have one equation which is relating the electric field at a distance r. That is E at r is equals to minus dV by dr. But here x and y are given separately in terms of the electric field also and in terms of the coordinate also. So I am separating this r coordinates into x and y. So here I can write Ex is equals to minus dV1 by dx. V1 means the potential in the x direction, right? The potential due to the x coordinate of the electric field. dV1 means here V1 is the potential due to this component. So I can write Ex is equals to minus dV1 by dx, and Ey, that is this Ey, which is given as minus dV2 by dy. That is potential due to this component is dV2. Now this dV by dx I can write as minus delta V by delta x. Here minus sign is there, so it is as it is. And dV by dx I can write delta V by delta x. So here delta V1 by delta x. Similarly minus dV by dV2 by dy is can be written as minus delta V2 by delta y. So if I make here delta V as a subject, because it is asked to find the potential. So first we will find the potential due to electric field in the x direction and then potential due to electric field in the y direction. So I want to find first the potential due to the component of the electric field in the x direction. So then we get delta V1 is equals to minus delta Ex into delta x. Now delta x is this 2 minus 0, so it is 2, and here Ex is given minus 20, so here it is minus 20 into 2, that is minus 40 volt, and delta V, that is 40 minus 0, right? Here it is minus 40 there, so minus 40 minus 0, because at the origin the electric field is given 0. So here it is minus 40 volts. So we can write V1. Either you can write delta V1, then it is also okay, or V1 is equals to minus 40 volt. Similarly for this equation. So delta V2 is equals to, by making here delta V2 as a subject, so we can write minus E by delta Y. What is Ey given? Y component of the electric field? It is 30 into delta Y. Again same, 2 minus 0. So here it is 2 and minus 30 into 2 is minus 60 volt. So at this point, the potential due to X V1 is given minus 40 volt and potential due to the Y component of the electric field, that is V2, is minus 60 volt. Now what is the net potential at this point? So we know that potential is a scalar quantity, so we will add it directly. So delta V or only V. So V is equals to V1 plus V2, which is minus 40 minus 60, so minus 100 volt. That is, the potential due to this electric field is minus 100 volt. Let's discuss about equipotential surfaces. So what the term mean, equipotential surface? See, equi means equal and potential means potential. That is equal potential surfaces. So for example, suppose I have here a charge, a positive charge. Suppose I want to find the potential at this distance r. Then what is the potential at this point due to this charge q? It is given as kq by r. It's a formula of electric potential. Suppose I want to find the electric potential at the same distance r towards this side. Then this is our distance r. Then there will be the same potential, right? Because the distance of the charge is same as this distance. So these two distances are equal. So here the potential is same, kq by r. Let's call this distance as a r1. So this is r1, this is r1. Similarly, again I want to find the potential at the same distance but above the charge. So here it is again kq by r1. This distance is r1. Similarly, at this point, at the same distance, similarly here, at this point, here at this point. See, all these points are at the equal distance from the source charge. R1, 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 right? This is also R1. So if you join this here, you can make as many as point you can. So if you join all this point, what you will get? You will get a circular section, right? Circular surface. Now suppose if I take take same distance towards this side, means in the z-axis. See, these points lie in the x-axis, this point lie in the y-axis, this point, and these points are lying in the xy plane. Now suppose I want to find the potential at the same distance r1 but in the z-axis, right? Then I will get the same potential. Now if you connect all these points, what you will get? You will get a sphere. So this sphere, at all point on the surface of this sphere, you will get same potential. So you can say that this surface, this whole surface is having an equal potential, and this surface is called equipotential surface. That is, if you place a charge at the center of the sphere, or there is a charge and you assume that this charge is at the center of the sphere, and you make a sphere of radius r1, then you will get a surface in the 3 dimension, and that surface is called spherical surface. Now if you find the potential at each point on the sphere, then at every point on the sphere, then you will get same potential. Then that whole surface is called equipotential surface. That is, if here the potential is of 10 volt, then here it will be of 10 volt. At all this point, at every point, the potential will be same. Now suppose I want to find another equipotential surface. Then suppose I am taking this distance r2, right, and the same distance here r2, same distance here r2, same distance here. Now if I join all this point on this line, then I will get another equipotential surface of radius r2. That is, if I imagine that as a sphere of radius r2, then at all this point on the sphere, right, at all the point on this sphere, the potential will be same. For example, here we have 10 volt. So here let us assume that here the potential is 8 volt. So here at all this point, that is at every point on this spherical surface, the potential is same. So hence we can say that this surface is known as equipotential surface. This surface is also equipotential surface, but this two surface doesn't have equal potential. This surface is equipotential because all the point on this surface the potential is same. Similarly, individually this surface is equipotential, but these two surfaces have potential difference, that is of the 2 volt. Why we call these two as a equivalent? Because here at each point the potential is same, that is of the 10 volt. Similarly, here at each point the potential is same, that is of the 8 volt. So this surface is called the equipotential surface. Now what are the properties? We will see other equipotential surfaces also. So what are the properties? First, same potential at every point. So this surface is equipotential surface. So at each point the potential is same. Similarly, this is another equipotential surface having less potential than this surface, right? So this is on this line at each point on the sphere the potential remain same. Work done is equals to 0. That is, if you move a charge from this point to this point here, right, then the work done in moving a charge on an equipotential surface is 0. How it is? We know that V is equals to W by Q naught, right? And what is V? It is actually delta V. So W is equals to delta V into Q naught. We have solved one numericals, right, related to this. So work done is equals to change in potential into charge Q naught. So this is our charge Q naught, which we want to move from this point to this here anywhere. Now the work done is equals to change in potential or potential difference into magnitude of test charge. So delta V, that is, here we have 10 volt potential, here also we have 10 volt potential, that is the potential difference is 0. So we can write W is equals to 0 into Q naught. That is, work done in moving a charge on an equipotential surface is 0, right? Then electric field is perpendicular to EPS, that is equipotential surface. That is, at all this point on an equipotential surface, at all this point, at each and every point on the equipotential surface, the electric field vector is normal, that is, it is perpendicular at all this point. That is, if you have an equipotential surface, then the field lines will cross it perpendicularly. So here we can say that electric field is perpendicular to equipotential surface. Why? We need to prove that. So we know that E is equals to minus dV by dr, that we have obtained, right? Then dV is equals to minus E dot dr cos theta. See, dV, it is a dot product, or E dot dr, it's a dot product. So for dot product we have cos theta. So dV is equals to minus E.dr cos theta. But dV means potential difference, very small potential difference. But as this is an equipotential surface, so the potential difference between any 2 points is 0. That is, dV is equals to 0. So we can write 0 is equals to E.dr cos theta. But we know that electric field, that is E at that point, is not 0. Also distance dr is not 0. So what is 0 there? The value of cos theta is 0. When cos theta is 0, when theta is equals to 90. So if theta is equals to 90, then cos 90 is equals to 0, then this whole term will be 0. So we can write E dot dr cos 90 is equals to 0. So we have proved this equation that E dot dr cos 90 is equals to 0. That is, the angle between the electric field and the point at that point, right, at this surface, the point, the angle is 90 degree. That is, electric field is perpendicular to this surface at each and every point. Closer the equipotential surface, stronger is the field. Farther the equipotential surface, weaker is the field. Now this we will see in the case of the equipotential surface due to a dipole, that we can understand it clearly. Then no two equipotential surface can intersect. That is, if two equipotential, suppose there is an equipotential surface and here another equipotential surface. So if these two surfaces will intersect at this point and at this point, then what will happen? there will be a total, that is the potential will get added. So at this point there will be a new electric potential. For example, suppose the equipotential, on this equipotential surface the potential is of 10 volt, and on this equipotential surface the potential is of again 10 volt, and at this point the potential will be 10 plus 10, 20 volt. So if they intersect, then you will find net electric potential at that point. So if at all this point if the potential is 10 volt and here it is 20 volt, then we cannot call this as an equipotential surface, and hence no two equipotential surface can intersect. Now suppose here you have a charge, and from that charge the electric field lines are coming out like this, or here you have applied some battery or something, and the field lines are coming out from this surface like this. So this all field lines are parallel. So when the field lines are parallel, it indicates the electric field is uniform. That is, at all this point the electric field is same. So here I am representing it in a one dimension, but if you want to represent this thing into two dimension, then suppose here, because as the field lines are coming out like this, so other field lines are also there, but they are behind this line. So here if I can show this, then one field line is coming out from this point in this direction, another from this point, this point, this point, this point, this point. So similarly for this line, the electric field lines are coming out from this point, this point, this point, right, from all this point. So these field lines in two dimension, right, or you can say in the three dimension, these field lines are moving like this. So if you find the electric potential at that point, right, from this distance, then this distance is r, then at this point the electric field is kq by r. Similarly, this distance is also r, so at this point the electric field is kq by r. Similarly, at this point it is kq by r. So this line represents the equipotential surface in one dimension, but in two dimension, right, or in three dimension, this line means it is passing like this, right, but I want to find the equipotential surface which is in the three dimension. So if we extend this line in the backward or in the forward direction, then we will get like this. So this is the equipotential surface. This surface is the equipotential surface. That is, at all this point, the electric potential is same. For example, here we have 50 volt. Then all this point, at all point on this surface, the potential is same. So we can say that this is an equipotential surface. Similarly, if I move ahead, then the potential reduces and it becomes 40 volt. So now if I place here, then at all this point the potential is same. So this is also called an equipotential surface. This surface having potential of 40 volt, this surface having potential of 50 volt. Suppose if I want to move 2 coulomb charge from this point having 50 volt potential to this point, then what is work done? From this point to this point I want to move, then what is the work done? We know that work done is equals to delta V into Q naught. Now what is the potential difference between these 2 points? See, this is an equipotential surface. So the potential difference between these 2 points is 0, that is 50 minus 50. So work done is 0. Now suppose if I want to move a charge of 2 coulomb from this point to this point, then what is the work done in this particular situation, right? So what you will do? You will find this hypotenuse, right? And that's a very big mistake. See, this is an equipotential surface. This is also an equipotential surface, right? So if you take a charge from this point to this point, or in this way, or directly this way, right, we know that electric field and electric potential, all these quantities are conservative quantities. So it does not depend on the path, right? So if you take it like this or if you take it like this, it remains same. See, what is the potential difference between these 2 points? Here we have 50 volt and here this is also an equipotential surface. So here it is also a 40 volt. So what is the work done in bringing a charge from this point to this point? So we know that W is equals to delta V Q naught. Now what is delta V? Delta V means V2 minus V1, that is 40 minus 50. So it is minus 10 into 2, that is minus 20 joule. Similarly, if I am taking this charge from this point to this point, then the potential difference is same. See, 40 minus 50 minus 10 and charge is 2 coulomb. So you don't need to consider the direction, you just need to consider the potential difference between these 2 points. So work done is equals to potential difference between these two equipotential surface into the charge, right? So in the upcoming, so after few minutes we are going to solve some numericals related to this, so don't get confused, right? Here the work done is equals to potential difference into charge. Don't see the path, just see the potential difference between the two surfaces. Now let's see equipotential surface of a dipole. This given picture represents the equipotential surface. Here each line represents the equipotential surface. You can see here there is a white line. The white line is actually a three-dimensional or two-dimensional plane surface. You know that the electric potential on the equatorial line or on the equatorial plane of a dipole is 0. So that white line represents the equatorial point, where at each and every point the potential is 0. That is, it is the equipotential surface. Here the blue line or the blue circle represent the another equipotential surface, which is of 5 volt. That is, each point on this blue circle represent a potential of 5 volt. That is, everywhere the potential is same, and hence this surface which represented by blue line is called the equipotential surface having 5 volt of potential. Similarly, the line or the circle near the negative charge shows a potential of 10 volt. That is, each point on that circle have a potential of 10 volt, and hence that surface is called equipotential surface. Also, you can see that in between the two charges, the field lines are closer, which indicates that the equipotential surfaces are closer. That is, the potential is stronger in between the two charges, while as you move away from charge, the potential decreases. Now let's see equipotential surfaces of two identical positive or negative charge. Here you can see that the blue line represent or the blue circle represents the potential of 10 volt. That is, at each point on that blue circle the potential is of 10 volt, and hence that surface is called equipotential surface. Similarly, red circle represent the potential having 20 volt. That is, at each point on that circle having a potential of 20 volt. Equipotential surfaces are far apart in between two identical charges, indicating weak field, and equipotential surfaces are closer on the either side of the charge, indicating strong field. A uniform electric field E of 300 Newton per Coulomb is directed along negative x-axis. A, B, C are 3 points in the field having x and y coordinates in meter as shown in figure. Find the potential difference VBA, VCA and VCB. Now according to the given question, here this is our y-axis and this is our x-axis, and the electric field is directed towards this negative x-axis. We need to find the potential difference between point A and B, that is VBA, and potential difference between C and B, and potential difference between C and A. So we know that VBA is equals to VB minus VA, that is potential at B minus potential at A. So see, these field lines are moving like this. So this is our equipotential surface. It is acts like this. See here, this is our equipotential surface. In 3 dimension, this is our equipotential surface, and the field lines are moving in this direction. Right? So this is the direction of the electric field. So if you place a book or anything here, if you imagine a surface here, right, then this is our equipotential surface, this line, because at all this point the potential is equal. So if you bring a charge q naught from this position to this position, then the potential difference between these 2 points is 0, because they both have the same potential. For example, let us assume that here we have potential of 1800 volt. Here also we have 1800 volt, just for our assumption. And what is the potential difference? 1800 minus 1800, that is 0. See, potential difference is 0. Potential is not 0. And what is asked? Potential difference. So potential difference between these 2 points is 0. Now, potential difference between C and B. So we know that V is equals to, or we can say delta V is equals to minus E dot delta X, that we have derived. What we have derived? V is equals to ED, or dV is equals to minus E dot dr. So this is the modified equation, right? So delta V is equals to minus E dot delta X. So delta VCB, so delta VCB, that is the potential difference between C and B. Or you can also assume that work done in bringing a charge from C to B. See here, this is the direction. In this direction, the electric field decreases because it arises from this side. So this is the higher potential, this is the lower potential. You are bringing a charge from lower potential to a higher potential. So in that case, the potential will be negative. Why negative? Suppose here the potential is lower because electric field is moving in this direction. So it arises from somewhere here. So at this point the field is stronger. As you move this side, the field is decreasing. So this point is of higher potential and lower potential, and this point is of higher potential. So what is the potential difference between these 2 points? So here VC is at the lower potential and VB is at the higher potential. So if you subtract a small number from a larger number, the answer will be negative. So your answer VCB should be negative. If it comes positive, then your answer will be wrong, because you are subtracting lower potential, you are subtracting higher potential from the lower potential, that is VC minus VB. So delta VCB is equals to minus E dot delta X. This is the equation we are having. So here E is minus 300. See, minus sign, what is electric field in this direction is given? 300 into 7. That is, what is, why 7 it is? How much distance? What is the difference between these 2 points? This distance up to this point, it is 4, right, on the x-axis. See the distance on the x-axis. This distance is 4 because this is 4, 4. So this distance is 4 and this distance is x-axis, it is minus 3, that is 3. So the distance between these 2 points, the displacement, the shortest distance, the straight line distance between these 2 points is 4 plus 3, 7. So delta X is 7. So minus 300 into 7 is minus 2100 volt. That is, the potential difference between these 2 points is minus 200 volt. Now it is asked delta VCA, that is the potential difference between point C and A, this point. That is VC minus VA, that we have to find. Delta VCA means VC minus VA. So VC minus VA. But here VA and VB lies in on a same equipotential surface. Hence the potential, because again see, this surface is having an equal potential. So this whole surface is an equipotential surface. So if you bring a charge from this point to this point, or from this point to this point, right, the work done will remain same. Similarly, if you bring a charge from this point to this, or from this to this, anywhere, because this whole line is again an equipotential surface, this surface is again an equipotential surface. So if you bring directly here or here or here, anywhere, so if you are taking a charge from one equipotential surface to another equipotential surface, the potential difference between any two points between these two surface, any, suppose between this point and this point, between this point and this point, any 2 point, the potential difference between any 2 points between these two surface is the potential difference between these two equipotential surfaces. So here Vc minus Va, but we know that Va and Vb both have the same potential. So Va is equals to Vb. So we can put Vc minus Vb. Now what is Vc minus Vb? Vc minus Vb means this. This we can write Vc minus Vb because this is Vcb. So it is delta Vcb. Now what is delta Vcb? It is 2100 volt. That is the potential difference between these 2 points is minus 2100. This 2 point is also minus 2100. Same here. So that is the potential difference between this equipotential surface and this equipotential surface is minus 2100. Now in the next lecture we will discuss about electric potential energy due to a single charge, due to a system of charge, in the absence of an electric field and also in the presence of an electric field, and also we will discuss related numericals. I hope you have enjoyed my lecture. Please share, subscribe, like and give your feedback in the comment section. Have a nice day.